So welcome everyone again. I would like to make a short video about this linear potentiometer. I made some upgrades regarding the potentiometer, so I want to share it with you. And in the last time I was showing the demonstration with a logarithmic potentiometer instead of a linear one, but now I purchased a linear potentiometer, so I can show you the data more precisely and in the way as I wanted to show you originally. So let's talk about the things again, just to refresh the things. So here I have this Arduino Nano in an extension board. So it makes very simple to screw the wires in it, so you don't have to struggle with soldering or anything else. And then here we have the ADS1115 4-channel 16-bit analog digital converter. It uses this I2C transfer protocol, or whatever it is called. So basically you just need two wires, the data wire and the clock wire, and of course the power wires, to connect it to an Arduino. So it's very simple, and it can be used in single-ended mode. So you use the 4 separate channels plus the ground to measure 4 different sources, or you can use it in a differential mode where you use the inputs in pairs, so A0, A1, A2, A3 as 2 separate channels, and then you can have better resolution, less noise and stuff like that. And then this is a LM317T based voltage regulator. This is the chip, and this is a trimmer potentiometer. So basically you can set the output voltage of this circuit by turning this screw on the potentiometer. What I do here is that I regulate the 5 volts output of the Arduino with this in order to reach 2.08 or roughly the same voltage, because then I can shift the source voltage for the potentiometer, and I can use different PGA setting for the AD converter, and by doing so I can use the 16 bits of I can use the 16 bits of resolution in a smaller voltage region or range. So let's say the original voltage range for this AD converter is roughly between plus and minus 6 volts. But if I change the PGA setting, then I can go down, let's say in this case, to 2.0 something volts. And what this means is that I can narrow down the voltage range to plus minus 2 volts, but at the same time I can still use the 16 bits, which means that I have a much smaller range, which I can then split up to the 16th power equal parts. So in principle here I'm using the positive part of the range, therefore I have to divide the number of available bits by 2 as well. So in principle I'm able to distinguish 32,000 different levels for this potentiometer now. That means that I have like 62.5 microvolts per bit resolution if everything is like idealized. So what I am doing here is now I'm using a different potentiometer. I just quickly soldered it, so that's why I have these cables. So let me show you that I made this small 3D printed part. It's basically just a case for the potentiometer. So as you can see it here, now it's already attached. It's very solid. What I want to do with this, that I wanted to raise the potentiometer so I don't have the problems with the legs, and also I have this very nice flat surface so I can glue on it, glue on something, what I will do in the future videos, so I will show you. So it's a very firm piece of plastic, so it's not snapping or not breaking. It took me like 20 minutes to print it, and it's more or less good quality. So for this I will remove the cables and then I just snap it in, and I will glue this against the surface. But now what I want to show you that I will make some readings. So basically now the potentiometer is at the 0 point, and if I move in this direction, then I'm increasing the output voltage. So what I want to do now is basically a very coarse calibration of this. So as I mentioned in the previous video, I can do like two kind of calibration. One is like without doing any, let's say, scientific measurements. So I say that I just base everything on the data sheets. So I say that the travel of this potentiometer is 6 centimeters. So this is the 0 position, and this is the 6 centimeter position. And I also know that we start from 0 volts and we end up with the 2 volts, which comes out from the regulator. And then we also know that we are just using the positive part of the range of the AD converter, which means that I divide this 6 centimeters into 32,000 and something equal parts. So basically I can say that if the number of bits is, let's say, 0, then I am at the 0 position, and if it's the maximum, so 32,000 and something, then I am at the maximum position. But in this case I will do a more careful thing. So I say that, okay, this is the 0 position, so this is calibration type 1. So we are at 0, and meanwhile I'm running my computer and I can see the data. So actually at this point the bit is 518, and then the corresponding voltage is 0.0323, let's say. So bit was voltage. So now I have this, and I can move to the maximum position now, which is basically, let's say, the 60 millimeter. And now I have 32,767, and now I'm reading 2.047 volts, and actually it's not changing. So these are like very precise. So with this I will do it on the screen somewhere, but I just quickly show it here with the drawing. So I can do something like this. So I can see that say that, okay, let's make this can be either the bits or the voltage, but I would rather use the bits, because the bit is the first number you get from the AD converter, and this is already multiplied by some number, so you can have a very small numerical error when you go from the bits to the volts. So let's just choose the bits. So we have 2 points, and also we have the distance. Let's just in millimeters or whatever. Now we don't really care about the units, but we have this, and then we have 2 points, one, and we assume that this is linear. So this is like the 500 bits, and let's say this should be the 0. So the 0 actually starts here, and this is like 518, and then here the distance is 60 millimeters, and the bits is 32,767. And we just fit a linear slope on this, and we say that, okay, we read whatever is this, 16,000, and then that should be 3 centimeters or 30 millimeter or something. So you just get the equation. So basically the equation of this linear here, and you just substitute the numbers, and you can get the distance from the bits. So this is like the quick and lazy way to do it, and maybe less precise, but you can also take a caliper. Now I'm using a very bad Chinese, okay, Chinese does not necessarily mean bad, but I'm using some yeah, Chinese stuff. So the resolution is like 0.1 millimeter, and the accuracy is 0.2 millimeter. So this is like the worst possible caliper that you can buy, but it's very cheap, and it's plastic, so not so rigid, it's not so reliable. Also the grips are very bad, I would say. They also have a small gap there, but let's not talk about this now. So the other way that you can do is like basically you do the same way, but let's say that you start at 0, so this is your reference distance, and now I just want to do like, this is already bad what I'm doing here, but I'm just measuring the distance. So the side of this housing and the end of this pin, or whatever is this slider here, so it's like 12 point, so this is our reference distance, which is the 0 is 12.8 millimeter, and now the bits is 497. But the bits already changed a little bit as compared to the previous reading. But let's, and now we can do like, okay, let's increase the distance to the maximum just for fun. So I try to measure it again between the 2 parts. So now it's at the maximum. So we traveled we are at the 68.7 millimeter, and now this is the same maximum, 32,767. And now what I will do is totally random now. So I just move to this position and a little bit squeeze it so they touch for real. So now this is 20.5, and let me write this down. And now I'm reading actually 4,835. So now I increase the distance again to some random. So this is not, so okay. So now this was 33.2 millimeter, and this is 12,000 and 49. Now increase again, and then just squeeze these things together. So 43.8, and now we are at 18,349, and just do a random last one somewhere nearby the end. So $57.7, and this was at 26,519. So I just made basically 6 readings. So what we expect is that we have the distance and we have the bits, and then these things are scattered like this, so we can fit a linear on this and do the same thing as we did previously. So we have the linear equation, we just substitute the numbers and get the corresponding distances. So what I do now is I move to the computer and analyze both things. So here we are. I'm trying to evaluate the measurements. So let's start with the first one, where I just noted down the bits for the 0 position of the potentiometer and the maximum position for the potentiometer. So if you remember, then the bit for the 0 position was 518, and then for the maximum position, which is 60 millimeters, it was 32,767. So what I did is basically I just plotted these 4 numbers on a chart or a graph. So here is the 500 and here is the 32,000, and I just fitted a linear equation on this, and let me show it. Not this one, but this one. So basically this is the equation of this slope here. So what you do is you move your potentiometer, you read the bits, and you just substitute the x with the number of bits. So let's say you write 16,000 here, and then the solution of this equation would be somewhere around 30. So you just use the equation, writing the number of bits to the x, and then you get back the distance. So where is the potentiometer right now? And then I did another thing. So in this table you can see 3 columns. The first one is the bit for the corresponding position of the potentiometer. This is the position which I measured between the side of the potentiometer and the wiper. And then the third column is basically the corrected or shifted position. So basically I said that the first position is the 0, and then the distance between the side of the potentiometer and the wiper was 12.8. So I just subtracted 12.8 from these data. And then this is the plotted number. This chart corresponds to the selected 2 columns. So this is without any correction. So you can see that the first position is here at 12.8 millimeters, and then increasing, and we are at the final position. And then also the red line is the fitted linear equation, Let me find it. Yes, it is this one. So you can see that here is the x. So basically you just use the equation from this sort of calibration. You substitute some number here, the bits, and then you get the solution of this equation as the position or the distance. But this is not the... this can be used for relative displacement, because the distance between 2 points is okay to get from the uncorrected positions. But if you want to know where your slider is placed on the potentiometer based on the number of bits, you have to correct the numbers. So let me show that window. So this is the corrected, so basically the first column and the third column. So now you can get basically the absolute position of the Viper. So the same linear equation, basically the only thing that changed is the B coefficient, so basically the intercept. And let me show you that. It's not this one. Yeah, so this is the equation of the corrected one. So slope, intercept. So this is for the absolute position, and this is for the relative position. And if you can see, the two numbers for the slope are basically the same. The only thing that differs is the intercept. So this is basically, we shifted back the line or the linear slope to 0. So this is all. So if you just take some random measurements as for this middle column here, then you can get the relative displacement, and for most of the measurements are this is reliable and it's okay. And if you want to know the absolute position, then you just make this correction and you can know the absolute position for this. So it's very simple, and you can see it from the graphs. So I open just these two, that this potentiometer is really linear. And let me show you this as well. So I put this here and I put this here. So this is for the randomly read numbers, so the slope of this, and the other slope is for the minimum and maximum position. So if you take just two numbers and fit the linear on it, then you get a bit different slope. In fact, I can plot them against each other. So now the red one is still with the 2 points, and then the black one with the dashed line is for this window here. I'm just checking it. So with the more precisely calibrated thing. So you can see that you can get a little bit difference between the two numbers, but it's not that bad. And maybe I cannot decide which is better, but maybe I can improve the calibration, which I did manually, because I believe that it's wrong to some extent, because I just quickly did it. But you can see that the truth is between these two lines somewhere. And if you just have a small displacement, then the error is very small, or the difference between the two results. And then if you go around this position, you can see that you can differ by a few millimeters. But for these small displacements, it's okay. So this is what I wanted to show you basically. So you can calibrate your potentiometer with two different methods. Of course, this is not so official calibration, so of course you won't have very scientific results from this, but for DIY projects this is perfectly enough, and it's a very cheap and simple solution. And I hope it helped, and if you have any questions, just let me know, and I will try to answer them. So see you in the next video.